My name is NavinKumar. Today I'm going to talk about more about single event upset. Then how we are going to integrate this driver to in Zephyr community. So let's begin. So about me, I'm working as a FPGA firmware senior engineer in Intel Corporation. Since 2022 onwards, I'm working for Zephyr community. So I contributed few drivers like a NAND, reset manager for Intel IPs, then SEU and ILC drivers. So some three drivers already merged with Zephyr community. So first we will go with what is SEU. So SEU or single event upset, majorly due to this comic rays or some external event like kind of temperature. Due to that, it will flip flop the particular bit on the hardware. So it will not damage any hardware bits or something. Any hardware failures will not happen, but only the bits flip flop will happen. So it's also is a temporarily only, but it will not permanent damage will not happen anything. So for example, you can see before the memory look like this. So due to this external event or cosmic rays, the bit can be changed. So I already told it's kind of is a soft error. So once you reboot the system, it will not happen. So you can't able to backtrace. So you can't able to reproduce again back same error same time, but it will happen particular time. So then it will have the kind of lot of difference in your result also. So I have here some examples. So I took this example from internet, some newspaper. Okay. So in 2003, in Belgium have some kind of elections in municipality. So they used their computers and the magnetic both to pulling the vote. So that time the people are putted the vote. So after whenever the result came, that time they get the result of 4610. It's kind of totally the people count only there like around 3000, but they get voting count 4610. So that time the recounted using the magnet tape, and they found the total count of that person get only 514. So but the result came 4610. So they go through and they try to reproduce this count, but it's not happened again back. So then they go through that and they found out the result is due to this comic race, the particular 12th bit is changed to 1. Flip flop happened. So this kind of events it made very big impact in the elections. So like this, we have a lot of instance, example, you are using the energy meters in your home. So due to the heat temperatures, because of that, it can may flip the single bit, means you can get more number of bills, like instead of 100,000 rupees, you can get 10,000, 20,000. So that also might happen. So to resolve this kind of issues, we have the kind of mechanism there. This kind of SU errors totally have the two types of errors. It's a correctable and non-correctable. So correctable errors, we have the mechanism kind of BCH or ECC engines. These all the things are available currently. But this kind of things already part of the hardware. You can go for any RAM or any storage devices. Now currently it's available as a part of the your storage. But mostly you can see non-correctable errors, we can recover by rebooting the system. But it's only possible when you are in your data is in the RAM side. Okay, so whenever your data is present in RAM, so you are rebooting, then you can able to correct these errors. But if you are in the storage device, so you have the error recovery mechanism, but it's possible to corrupt. It's possible, but it's not happen. Your data will be corrupt. So there is no way if data is corrupted, we can able to recovery. But you have the single bit or multi-bit errors, it can able to possible to recover it. So it happen only reading time and writing time of the particular sectors. So why need SEU drivers in Zephyr? Actually, already I explained in the memory already have the external hardware device. So particular IP have the mechanism of error handling. But why need again SEU driver separately means it's because of FPGAs. Here you can see about FPGA. So FPGA is kind of field programmable gate array. In this, you can like after manufacturing the hardware, if you want to make any hardware or you want to implement any logics, you can design it and you can load it and you can use as a hardware. So even we can make processors also. So example, NIAS processor is a soft IP, so that is present and you can load it, you can use it. So in the FPGAs, what are the logic you are keeping? That will be stored in as a sectors. This area called configuration RAM. So in this area, all the data once whenever we are booting, that time data will be go and stored in these areas. So before I'm going to explain, so I want to explain like kind of in the FPGA process. So three important subsystems are present. One is FPGA fabric, another one is a firmware, and whichever the OS is running code, that is called OS core. So these three important areas are present. So what is the problem in currently in FPGA? So whatever we are writing the hardware logics, it will go and placed in the CRAM. So once it's placed in the CRAM, you can't able to read again because the hardware logic, so no one continuously go and read and write, they will not do. So whenever you are doing a read and write, then only your error mechanisms will work. So you want to compare your ECG values, ECC values or BCS value, you can compare any correction happen or not, you can able to identify it. But now in the FPGA processors is not possible because it's hardware logics. Hardware logics are placed in the CRAM area, so no one again go and read it. So to avoid this, they can't able to write any SEU errors also in that area. To avoid this, we have separate IP called Advanced SEU Detection IP. So this IP continuously it will go and read each and every sectors frequently time. So in this time it will read and it will monitor the always this FPGA CRAM areas and it will report it. So to I already shown you this kind of three subsystems are there. So they want to communicate with the Zephyr core, they need some driver. So to monitor that. So for that reason, like we implemented the SU driver in the Zephyr to monitor and share this information to the user. So mostly like in the Zephyr operating system, any error happen is correctable or non-correctable errors, it will handled by EDAC driver. So we are developing the layer below the layer of EDAC. So we will communicate with the external IPs and will share this information to the like EDAC driver. So it will be it will decision maker. Okay, it any non-correctable error will come, it will reboot the system. Its correctable errors means it will give it will store this information in particular region. So it will useful for next time. How much time it happened errors. So this is the driver model in the Zephyr. So mostly like device IPs, device drivers IPs are present in the community. So which are the vendors, IP vendors? Based on these IPs, they don't need to make the device instance and they will make the drivers. It will communicate. But already I mentioned that there is no need of SU drivers for other IPs. When it will come to FPGA process, then only is needed. So still now there is no SU drivers are present in the Zephyr drivers. So we implemented a few driver APIs to bring our concept into Zephyr OS. So that's the APIs are SU callback functions to register the callback functions. So example, EDAC want to communicate with the SU driver, they can register the APIs. So callback functions, one, it will monitor whenever error happen, so that which kind of errors it will report to that particular function callbacks. So same thing, like you can register and you can unregister the functions. Then after, like we have the APIs to inject the errors to like a validation purpose. If you want to validate any errors happen in the system, it can able to detect or not. For that reason, like we have some two APIs inject the errors on CRAM areas. So whatever CRAM areas is there, we can inject the error using this API, inject XU errors. Then after we have other APIs for inject the errors in SRAM of the software logics. So you want to use NIAS processor or inside soft logics, you want to inject any errors inside the RAM, you can use this APIs, we can inject the errors. So like this we can simulate the errors. So once error happen, again it will read it and it will call back function, it will call back. So you can get the information about what kind of error, how much time is consumed for this SU event. This kind of information you can get it through this callback APIs. Then like a process, actually, you've seen already the APIs are present, means then we can follow directly in GitHub, we can create the PR and we can merge it. But if you are developing the new API in the Zephyr community, you need to follow certain process. First, we need to create the RFC, is for request for comments. So you need to create your RFC ticket and you need to explain your architecture details, everything you need to explain it. Then it will go to the next phase for architecture review. Once this architecture review is completed, then it will go to normal PR process. Then your code will be merged in the Zephyr. So, thank you.